Hi guys, can you hear me, see me?
Yeah. Hello.
Okay. So where are the others? No. Where's
I don't think Tyler's coming. We have senior skip day, which means they don't have to come to school. Which, to be fair, means he should still be here, but I don't know.
so you're all seniors, right?
No, Dax
Both
and I
of
are juniors. We're juniors.
okay. Well, I could see the difference in the commitment. But we need to again. I posted all the assignments, so we need to get those assignments done quickly.
All right.
Because remember the assignments. If you don't do the assignments, the exam is going to be pretty. I mean, it's not difficult. It's exactly the same as the assignments, but it's just that if you try to wing it at the exam, you won't be able to do it.
Yeah, we saw that midterm.
I did, yeah.
Yeah.
So I don't think that's what we want to do anymore.
No.
Because I mean, it's a pretty straightforward, easy topic. The whole thing it's very logical, very easy. It's just that I don't know whether the commitment to doing the work is there yet. So, I mean, technically, this is what computer science is. It's a logical problem solving. How do we take a larger problem and solve it into small, discrete steps? Let me share the screen here. Can you see the shared screen?
Yeah, I can see it.
Yeah.
Okay. So before I get to anything new, so we have only like 2 more weeks. I mean, 2 more weeks before the end of the semester. Right, so there's a ton of work to be done, accumulated from past months. And so before I get to this, is there anything that you want me to review or go over it and see that, okay, that needs help?
Well, maybe not necessarily today, but I think going over the midterm would be helpful.
Okay. I'm going to send the midterms back to you.
Oh, okay, perfect.
Right. So I have posted the grades, but I mean I was as lenient as I can be.
Yeah.
Right. Other than that, I couldn't do anything else. Right. So, but you have to go back and compare the midterms with the homework assignments, and you'll find that they're fairly straightforward.
Yeah.
Right. If there was one coding thing that was a little tricky, was the swim and the sink. Right. Mm-hmm. Which is on the heap structures. Right. So let's do that. Maybe once you receive your thing, the midterms, we'll try to go through over that.
And just one more thing. I'm trying to look through the assignments right now, and I can't. I don't know if someone else wants to look at that, but anything past assignment 5 just is a blank screen. It doesn't load.
Does it download a PDF?
Maybe that's just my problem, but.
Can you check, and someone else check and let me know how it works? It's a PDF file.
I'm sorry, what were you talking about? I just
can you log in? Can you log into the assignments and see whether you can see the assignments? That is, can you see that there's a list of assignments after that?
Yeah, And assignment 6 through 11, I can see they're listed in the sidebar, but when I click on them, nothing happens.
On all of them?
Yeah, anything past 5.
Okay, let me then go back and see if I have to upload it again.
You should be able to get them as a PDF, but web just might be slow today.
All right. Well,
I can do PDFs if you want.
that'd be helpful.
I downloaded it.
Let's see if we.
Oh yeah, you know the same thing's happening to me, and I used to be able to look at some of those because I looked at 6 for sure. So this has changed.
So I'm thinking whether it might be a technical issue for today.
All right. Well, we can try it tomorrow and see if.
Or maybe later, because you're right. I mean, there's nothing happening on eCollege.
I don't know.
If not, what I'll do is I'll zip all the 6 assignments and email it to you, so that to all of you. So that might be easier too. But because I know, I mean, I'm not seeing anything either. So
Yeah.
I just see exactly the same thing you're seeing, a white screen. Even on the author mode, I can't see anything. This morning I saw a few things. Well, it's only your class that seems to be the problem, I think.
It'll just take a long time.
No, I think there might be a issue with eCollege.
All right. We can try it later and see if it starts working.
Okay, I'm just, let's see if something happens, but I don't see anything either. Right. So we're discussing network graphs, and so far what we looked at was that there are these graphs. We can call them directed and as like undirected graphs. How to represent graphs? The 3 ways of representing the graphs: using a list of edges. You can create a long list of edges, that would work. We can also create an adjacency list type of representation and an adjacency matrix representations. And what the advantages and disadvantages of each one of them. And then looking at all the 3, we chose to use the adjacency list. Right? And then the next thing we looked at was what is a depth first search. There are some basic definitions about a path, a cycle, what is degree of a vertex, a few things like that. And then we looked at what's called the breadth first search and a depth first search. Right? How do we do a depth first search and a breadth first search? In the depth first search, it's that you start visiting from the source node, but as you visit the nodes, the visited nodes are put into a stack. First, we mark them as having been visited, and then we put them into a stack, and then pull them out and start visiting the neighbors like that. It was a depth first search. For the breadth first search, it was the other way around. We put it. I mean, it's the same process, but we put this into a queue. We put it into a queue and then start visiting nodes, pulling nodes out of them one by one. That's what the breadth first search was. So those two things. And the last thing we looked at was in the directed graph, we looked at what's called a topological sort. Meaning if the graph edges have no cycles, like a scheduling problem, we can create what's called a topological sort. And to be able to do that, we do a depth first search and list the nodes in a reverse post order. Right? List the nodes in a reverse post order. And the last thing we did was finding connected components that are connected. If it is an undirected graph, how do we find connected components? If it is an undirected graph that has components, and how do you find connected, the different components together? How do we identify them?
You just do like a depth first search and mark everything you go to?
Yeah. Start from any node, do a depth first search, and then all the nodes we can visit become one component, and then take a node that has not been visited yet, and then visit all the nodes from there. That will become another component. Like that, you keep doing that. Right? So in a directed graph, it required a couple of little things to be done before that. And the way was that the first thing we did was reverse the graph. Right? Reverse the graph. Do a reverse post order listing of the nodes. And then go back to the original graph and do a depth first search using that order. Right? So step one, do a reverse the edges. Step two, do a reverse post order using a depth first search on that reverse graph. Step three, go back to the original graph and use that listed order and do a depth first search. Do you remember that part of it? Try it out once. Those assignments are making you do it by hand at least once. And if you do it once, that's all you need. It's not like you have to, these are not topics that you have to practice different ways. In the math problem, calculus, there are so many different things to remember. Here, there's only one and only one. That's it. There's only one way of doing it. If it is insertion sort, there's only one insertion sort. There are no variations of insertion sorts. It's not, you can't confuse us anymore. This is it. It's applications that can be quite confusing, but the algorithms themselves, there's only one exact procedure for it. So that's what we did so far in terms of graphs. There are two more topics. I don't know whether we'll be able to finish both, but that's based on what we want to do here. One is called how to create a spanning tree. The other is shortest path. How to find a shortest path on a given graph. Like how do you find the path? We can find a path. Do we know some way of finding a path, shortest path, based on what we know already? Is there something we did already that can give you the shortest path?
Yeah, we can use a breadth first search.
Yeah, breadth first search. The breadth first search will give us the shortest path, except that it's going to give you the path based on number of hops, meaning number of things. It's not really, so if the cost on an edge is different, like suppose, for example, we have a graph as shown on this, then we have a cost that's different on the different edges. Right? So if that's the case, we have to modify the breadth first search a little bit. We have to go the same way, except we have to modify the edges. So that's what the shortest path is. There are two algorithms. One's called Dijkstra's algorithm. The other is called Bellman-Ford algorithm. We can take a look at them. Both algorithms are pretty easy to understand. So here, before we do that, so this is section 4.3. It's called a spanning tree. And what we want to do is we want to find out what's called a minimum spanning tree. So a spanning tree is a tree that connects all the edges, all the vertices, sorry, a tree, a connection. So a spanning tree would be like you want to select the edges such that you can visit all the vertices without creating cycles. Right? So an example of a spanning tree would be, it's going to extend out like something like this. This is a spanning tree. Right? So you should be able to visit all the edges, visit all the vertices by selecting a link. Right? So a spanning tree. So we want to find out a spanning tree is a subgraph that is connected and acyclic, meaning there are no cycles. We don't need redundancy. We want to just to be able to reach from one node to the other. For example, is tree a spanning tree, like the red black tree, any type of a binary search tree? Is that a spanning tree? Yes, it is, right? In a tree, is it possible to go from one point in one vertex to another vertex? In the red black tree, in the 2-3 trees, or in the binary search trees?
Like, can you traverse a tree?
Yeah, can you is there a path from any node to any node?
Yeah.
Right? How many paths?
There's going to be one.
Exactly one, right? From any node to any node, there's exactly one. That's what a spanning tree is. Right? A tree had where we were able to identify what's called a root, and then we went from there. Here also we can create a root, but it's the same thing. It may not look like a tree, but that's the same concept. Identify the edges that connects the entire graph and remains acyclic. And this time the graphs have costs. So what we are trying to do is we want to find out this is not a spanning tree, because if you look at the dark edges, it's not a spanning tree because it doesn't connect all the vertices. There's a gap here there's a little gap over there. It's not a spanning tree because it does not connect all of them. This one is not a spanning tree because it's cyclic. It has a cycle. And this is not a spanning tree either because it has a cycle, and this is not what we want. This one is a spanning tree because it connects all the vertices. And this is the spanning tree. So the topic today is how do you select the edges that creates a minimum spanning. For example, this could be a computer network. So these are the distances between 2 points. And you want to create a network that uses a minimum cost. So the cost is proportional to the distance. Like it could be cables you want to lay on the ground, and that's proportional to the distance between the two, right? So you want to be able to connect or a supply route that moves things from one place to the other. You want to build a street network, that's supply network. And your task is to find the cost to identify the edges that will give you the minimum total cost. And that's what a minimum spanning tree is. Go ahead.
Sorry, no, we just got an interrupting call. You're ignoring it.
Okay. Right? So that's what a minimum spanning tree is. So you want to find a spanning tree, because it has to span and reach all the vertices, no cycles, and the cost should be minimum. Okay? So before we can get to that, how do you represent a graph like this, which has a cost? Any suggestions on representing the graph which has a cost associated with edge? Is there any do we have to do any modifications to the structure itself? Can we use what we learned before?
Yeah. As long as there's a root, you should be able to get a path.
Yeah, no, I mean the link itself. Do you have to make any modifications to the edges themselves? Representation, the data structure.
Oh, you're gonna need a link from any child to its parent so that you can traverse backwards.
Yeah, but before, so no, in terms of like a graph network, so we have a graph network. So first thing would be to find a way to accommodate the cost on the edges. Right? So all we have to do is, can we do a adjacency list and add one more field to the edge saying that's the cost? Right? So we can maintain the list. So the edge is going to be an edge weighted graph. So what it has is, in addition to the two, each edge will now contain one more field called the cost or the weight of it. Each edge has the A node and the B node, the nodes that it connects to. Each edge is going to be represented by a class that has a node start, a node end. That's what we had so far before. This time we have to add one more field called the weight that tells you the cost of the on that edge. Other than that, do we have to make any other modifications? Not exactly, right? Can we just, I mean, the only the minor modifications we have to make to the class called edge that needs to have this. And of course, we can add additional methods that says, for example, this one gives you either one of the edge. Like if we say, if you have an edge and you want to find out one of the vertices connected to it, you call this one. If you have an edge and then if you want to find the other vertex connected to it, you call the other vertex. You provide the first vertex and it returns the second vertex. And all it does is, so if you have an edge and says, okay, I know the A node is 5, what's the B node? So you provide the A node and it'll give you the B node. Right? And if you can also create an additional method called compare to that compares the edge with another edge and returns -1, +1, or 0 depending on the comparison of the weights of the two edges. Right? So we may have to make slight modifications to the edge itself to accept a weight to it. Minor modifications like adding a field called weight and adding a method that says get weight and a compare to method. Will that be sufficient? Anything else we want to think of?
No, I think that makes sense.
That should be okay, right? That's all we need to do.
That would do it, right?
That would do it, yeah. Right? So we need to make a slight modifications and we can still use the same structure, the adjacency list structure, except to add that extra field to it. So there's really not much we have to modify to be able to accommodate the extra field to that. Those are the extra field is the weight of that, weight or the cost of it. Okay. So that's the little modifications. But the main question is, how do we find the minimum spanning tree? How do we go about identifying what the minimum spanning tree is? If you're given a graph that's very complex, how do you, what procedure would be, how would you go about doing it? Any suggestions? I mean, there are so many different spanning trees we can technically create. Right? I mean, we cannot keep trying all the possible spanning trees. We should kind of go in a more orderly way so that we can create it, and we just have to see what would work for us. Go ahead.
I mean, if the tree's balanced, that'll be more efficient, right?
But it's not a balanced tree type of tree. It's a tree, but this is a tree too, right? Let me show you. So this is also a tree.
Yeah.
Right? It's a tree, right? It doesn't have to be balanced. You can. So this is a spanning tree, because as you can see that there's only one path from any. If these are leaves, from any leaf to the other leaf, there's exactly one path. Right? So this is a graph essentially, but so there may be more than one vertex, edge connecting these vertices. We're just choosing the ones that we want. We want to be able to choose the ones we want to be able to create it. For example, going back to the previous one, like we could have selected any one of these edge. How do you identify the ones we want, the ones that give you the minimum cost? Like for example, we create one spanning tree and determine what the cost is. This one has a cost. The cost is the sum of all the edges connected to it. Right? That the cost of that would be 50 plus 4 plus all that stuff. That's the total cost. The brute force way would be try all the spanning trees. Like for example, let's take this one out and maybe try a different spanning tree, and take that one out and take a different spanning. Like there are so many different spanning trees we can create. But is that how we want to proceed, or is there anything else that would help us find it in a more efficient way? So, I mean, before we go, I mean, these things, like they've got a list of applications where it's being used, right? Including dithering, which is graphics processing, clusters, real-time face verification, and a whole lot of things that we use minimum spanning trees to work to use in applications, right? It might look very straightforward and easy, but it's got its own application. So one of the things I'm trying to this thing is, let's see whether this assumption would work. Now, a cut. Define what a cut is. A cut in a graph is a partition of its vertices into two non-empty sets. That means if you have a graph like the one I shown here, you can have any number of cuts. A cut is like just cutting through this. Just cut through the graph. Right? Cut through the entire graph and create two non-empty sets. It's a lot easier to visually look at it and make a cut. Certainly, it's a lot more difficult to make a cut in a computer program. But I mean, actually, visually, that's what a cut means. A cut is cutting the graph into two sets of vertices, non-empty sets of vertices. Now, what we would like to postulate or propose here is that given any cut, you can take any cut, a crossing edge. So if we take a cut like this, right, given the crossing edge from one cut to the other And each of these edges have a different cost, a different weight. Right? Each of the edges allow, if you look at the graph, all the red edges, each of them have a different weight. Those are all the crossing edges, the edges that go from, take you from one set to the other set. Those are the crossing edges. Right? A crossing edge is an edge that connects one vertex from one set to another vertex on the other set. That's called a crossing edge. Are we okay with that so far? What is a cut? A cut is a thing that separates the edges into two separate sets. Sorry, the vertices into two separate sets. And a crossing edge is an edge that connects one vertex in one set with another vertex in the other set. Now what we say here is that if you take all the crossing edges, and what we are proposing here is that the postulation is that the crossing edge of all these edges, the one that is going to be in the minimum spanning tree is the one with the minimum cost. Like so we are going to, so the crossing edge in a minimum spanning tree would be the one with the minimum weight. That's what we are trying. Does that make sense? Or do you agree with that?
Yes, I see that. Because within each subset, they all need to be connected anyway. Okay. So you can be connecting from one subset to the other at any point. Yeah. You do the cheapest one.
You just have to take the cheapest one, right? Because by definition, that's how it needs to be, because all you need to connect is one of the vertex from one to one of the vertex from the other side. So therefore, if you take a cut, any cut, you can take any cut, and then in any cut, the edge that's going to be included in the minimum spanning tree is the one with the minimum cost. And as you said, yes, the proof is a longer way of describing exactly what we said. Well, if it is not, like if the edge is not the minimum spanning edge, is the edge with the minimum cost, then certainly we can replace the one with the longer one with the one with the shorter cost, because with nothing else changing on either side. Like if let's say, for example, if you're taken the cost f to be in the minimum spanning tree, then by it contradicts, it is not the minimum spanning tree because the edge E has a smaller cost. So we can replace the edge F with the edge E. Therefore, we can get to the minimum spanning tree by using the one with the minimum cost. Right? So all we have to do is find a cut, which is find any cut that separates the vertices into two sets. Look at all the edges that's going from one set, all the vertices from one set to all the vertices on the other set, and take the one that's the minimum. And keep repeating it forever. Will that work?
It should.
Yeah, it should, right? I mean, if you, the only question would be, how do you identify all the possible cuts?
On any given tree?
On any given tree. Like, so we need to cut. So like, for example, identifying every cut, you have to identify a cut like this, the one shown here, and take the one that's the minimum cost. Come on.
So could you just cut at every vertex, like every vertex?
start from one vertex
Yeah.
and then extend it like that. Go ahead.
If you cut every connection, like if you cut along every connection, just successively.
Like start from one and then cut this, take all these edges like that.
Yeah.
Yeah, that's what we have to do. That should work, right? You're a little late, but if you had told this earlier, we could have named it after you. Right? But that's what Prim's algorithm is. So essentially, that's what minimum spanning tree is, and it works off the same principle. So there are two different people proposed exactly the same thing. That is, how do we go about identifying the possible cuts? And how do we do that? And one is called Kruskal's algorithm, and the other is called Prim's algorithm. Right? So let's see how these things work. Let's say, for example, let's start with Kruskal's algorithm, and then we'll see what happens. Yes? So let's say, for example, the underlying concept is the same, that we are going to choose the edge with the minimum cost. Right? So in one algorithm, in Prim's algorithm, we would do what you suggested, start with the one vertex and then start building off that. Like start with a vertex, start with a given vertex and start building off that. In Kruskal's algorithms, let's start with an edge and see whether that edge needs to be included or not. So the algorithm itself goes like this. Let's arrange all the edges in an increasing order. Let's arrange all the, oops, what happened here? Right? Let's arrange the edges such that the cost in an increasing order of the cost. That's task number one. So we could create use a priority queue to do that. If you put all the edges into a heap, right, into a heap, and then if you throw it into a heap and start removing from the top, you can get the edge with. That's what the heap is, right? A heap is the one that can. So when you remove from a heap, what do we get? The one with the maximum priority or the minimum priority. That's what a heap is. And so that's exactly what we are going to do. Put all these edges into a heap and remove the one with the least cost. Let's take the first one out. Take the first one out and connect these two, 0 and 7, and see whether connecting these two, are these two vertices in the same component? Meaning, are they in the same set? So initially, they were not in the same set. They were like we can put them into, we can create many cuts. Right? Now, let's identify these two and say, okay, are they in the same, like a union find algorithm to see, like, are they connected to each other? If they are not, let's include the vertex into the minimum spanning tree. Take the next edge, 2 to 3. Let's add that. 2 to 3, should we include in the minimum spanning tree? Right? 2 to 3 we have. So if yes or no?
Yeah, we could add.
Yes.
We could add that. I mean, if you want to extend the definition of a cut, what I'm saying is, if you create a cut that consists of 3 only, and all the other nodes on the other set. One set consists of the node 3, and the other set consists of all the other nodes. So yes, 2 to 3 has to be included. Take the next one, 1 to 7. 1 to 7, include. take the next edge. 0 to 2. Include or not?
Yeah, we should include it.
Include it. Right? 5 to 7. Include it. 1 to 3.
No.
Don't, right? Because it's already there. We don't need that. Because now that doesn't, because that we already have a cut. We already have a path. Right? Now 3 also connects to. So if you take this as a cut and says, okay, there's a cut that's one side is 3 and the other side is all the other vertices, but we have already selected the one with the minimum cost. So therefore, we don't have to select the next one. So we don't select it. So don't select 1 to 3. 1 to 5. No. 2 to 7. No. Right. 4 to 5.
Yeah.
Yes, 4 to 5, yes, right? And then 1 to 2. Where's my 1 and 2? No.
No.
4 to 7.
No.
No. 0 to 4.
No.
No. 6 to 2.
No.
Yes.
Really? Oh, okay.
6 to 2. Right? And then 3 to 6. No. 6 to 0. No. And 6 to 4. No. That's it. What we have is a minimum spanning tree. Right? And of course it's so straightforward to do that. The only convincing proof is that the edge with the minimum cost should be included in the. So if you take any cut, such that it consists of 2 sets of vertices, the minimum spanning tree will contain the edge, the crossing edge with the minimum cost. Right? So does this algorithm follow the same principle, or what we, right, the min cut property? Does it? I mean, like for example, if someone says prove that this works, if someone says, okay, I can arrange all these things, I can arrange all this, I can arrange the vertices in an increasing order of the cost, and then go through the list and pick the vertices, the edges I want, edges in the increasing order, pick the edges I want. And if someone says prove it, it's easy. Now the algorithm itself is pretty straightforward. There's nothing that's, I mean, of course we could have come up with the proof easily. I mean, the algorithm, right? But the question is, the proof requires us use the min cut property. Why does it work? Why does this thing work?
I mean, you're always going to get a connection with it.
I'm always going to get a connection, yes. But the question is, why do you think the cost would be the minimum spanning tree cost?
Because every time we try it, it's like doing a cut, like cutting out one vertex. And then we know that the edge we're looking at is the cheapest one because it's appearing higher in the list.
Exactly. We have already arranged the edges in an increasing order, and then we are going to say that so we just every time we look at exactly what we are doing is to see, okay, let's even when you start off with and says, for example, you take the edge and says, okay, is this a crossing cut? Every edge is a crossing cut, but then have you already identified the minimum cost? If you have already identified the minimum cost, we don't need to include that. And why is it minimum cost? Because the edge that's identified first, because we have listed them in an increasing cost, we would start identifying edges in the minimum cost order. Right? So this is one of the algorithms, which is to say, yes, let's arrange all the edges in an increasing cost and build off that. Take the ones we want, throw the ones we don't want. Another possibility would be to see like kind of how Justin suggested where's my other one? Is to go the other way around and list all the edges and start from one of the vertex. Let's say you want to start from vertex 0. Right? Start from a vertex 0 and say, let's identify this as one set. Let's identify that as one set. And what's this? Right? Let's identify that. Right. And identify a crossing edge. Right? Actually, I'm going to go here. Right? This helps better. That's a crossing cut explanation. So let's identify. That the one then what we showed was this is actually the that's not what I want here. Oh, demo greedy. Sorry, wrong slides. Okay, this is what we need. So let's start from here. These are all the vertices, these are all the edges and the cost. Right? Let's identify one vertex. Let's identify a cut that includes this vertex, 0 on one side, and everything else on the other side. Right? That's a cut. Right? Vertex V 0 on one set, and all the other vertices on the other set. And find the crossing edges. This is the list of crossing edges. Right? Make a list of crossing edges and select the one with the minimum cost. So we select this one. And what do we do next now? What do you think we'll do next?
try another cut.
Which cut? How do you want to select how do you want to select the other cut?
Another one from that vertex, or
So
one of those connections. So you could go 0 to 2.
why don't we do this? Let's put 0 and 7 on one side now.
All right.
And then find a cut that's all the other nodes on the other cut. We have a cut that's, 6. Right? So now that we know that 0 and 7 are connected, we have already identified the cut that's minimum. Let's put 0 onto move 7 into onto the 0 side. Now let's find all the edges that go from connect 0, 7 to all the remaining vertices. So that means we have to add the extra vertices which were 0, 7. So that means we'll have to, right?
Can we use a priority queue for this too?
We use a priority queue, except that we need to know the cost. I mean, we have we need to identify. So once we include 0 and 7.
Right. Once we include 7, now we can add all of 7's edges to the queue.
That's right. Add all the 7's edges that's added to the queue. Right, and then so now use a priority queue because we want to identify the one with the. So these are the crossing edges now. Edges that's crossed from 1 to from 0 all the way to the other side. Sorry, that we should 7 is not connected, but this is after connecting it. But before we connect it, so there's so we have a list of edges that goes from 0 to the other set, and a list of edges that go from 7 to the other set, and select the one that's the minimum cost, which should be that one. We need a priority queue because we want to get the minimum cost. So that makes it this one now. Right? So now we have 0, 7, and 1 on one side. Right? So 0, 1, 7 on one set, and all the others on the other set. 2, 3, 4, 5, and 6 on the other set. And we proceed the same way. Right? Now find all the crossing edges. Right? Find all the crossing edges between 0, 1, 7 and 2, 3, 4, 5, 6. That means we'll have to add the extra edges, which will be this one, that one, and this one. So we add the edges. So we have added. So minimum spanning tree contains the edge 0, 7, 1, 7, and then all the list of edges. This is the new list of edges. That's the new list of edges. And that's the one with the minimum cost. We select that. Right? So now we have a set that consists of 0, 1, 2, 7. Another set that consists of 3, 4, 5, 6. So add the newly discovered edges into the heap. Right? So as we discover a vertex, add all the newly discovered edges into the heap, and then proceed similarly. Right? So this is what we have so far. Add the so this is the new list of the new list. and proceed similarly. Right? So now which we take 2 to 3, so we take that one. So we have a set that consists of 0, 1, 2, 3, 7, and another set that consists of 4, 5, 6. And then the spanning tree looks like this. And then this is the new list of edges. Select 5 to 7. Right? That's it. It's as easy as that. Right? So when we have a new list and we select 4 to 5, and select, that's the new list. Then we select 2 to 6. Right? So this is what's called Prim's algorithm. One was Kruskal's algorithm, the other is Prim's algorithm. And in one of them, we kind of, in Prim's algorithm, we start with a set and then start expanding the set of vertices. It was expanding based on, like, okay, let's start from here with a set that consists of one node, and then try to find the crossing cut for that, and then expand the set as we expand. Whereas in Kruskal's algorithm, we listed all of them in an order, list all the edges in an order, and start selecting the ones we want, ignoring the ones that would create a cycle. Right? Go ahead, Justin.
In Kruskal's, you list out our edges in order of increasing weight.
Increasing weight, yes. And here also we are going to do the same thing, but we are going to look at edges. They are going to look at the, but not. They're going to list the edges of the crossing edges only. There we listed all the edges. Here we are going to list only the crossing edges. And then select the one that has the minimum cost. Right? So it's pretty straightforward. In this entire chapter, the only thing that requires any kind of, something interesting or challenging is the Kosaraju's algorithm. There's nothing challenging here. The idea that's challenging is what is the minimum, what is a cut, and what is a crossing edge, and then the property that in any crossing edge, any set crossing cuts, the edge with the minimum cost would be included in the minimum spanning tree. Right? So if you take any cut and you identify all the crossing edges, the one with the minimum cost will be included in the minimum spanning tree. Once we are convinced about with that property, the rest of the thing is very mechanical. Computer programs all, go ahead.
I was just going to ask, which of the algorithms is better or faster?
So we'll look at that. We'll look at how we can implement it. And we'll look at the implementation on Wednesday. Right? We'll look at what the implementation is. So the assignments are straightforward, exactly as we discussed. So get your points that way. These are all handwritten assignments for most part. It takes like 3 sheets of paper, and a lot less work than a normal high school assignment. Okay, it's 9 o'clock, so I need to let you go, and then we'll see you back Wednesday.
All right.
Go
Thank
ahead.
you.
You're welcome.